Welcome to Aerodynamics. In the previous lecture, we looked at a group of streamlines that are issuing from a point source. And that group of streamlines, line 1, line 2, line 3, can be classified into a stream function. So a stream function is just a group of streamlines. So we will denote the stream function by psi. So all that family of y equal cx is our streamlines, but for variable c, you're going to get a different streamline. So with 2D flow, the relationship between the stream function and the velocity field is as such. The gradient of the stream function with respect to y gives you the horizontal velocity component in the x direction u, and the derivative with respect to x will give you the velocity in the y direction. There's a minus sign. So that's for 2D flow. And if you look at the radial coordinates, which we will come to, we will need to use those later on. You have the radial velocity component and you have the tangential velocity component, with r being the radial coordinate and theta being the angular coordinate. So that's the relationship between the stream function. So you define the stream function in Cartesian and radial coordinates. Okay, so what we're doing right now is we're building the last pieces of our toolbox that we will be using for our aerodynamic theory, or the basic aerodynamic theory that we will focus on in this course, which is the potential flow theory. So for us to understand what a stream function is and what it means and its definition, that's the purpose of this of these slides. So now let's look at the mass flow rate. Now the mass flow rate is defined as the rho VA. So now I can, if I have a velocity, I have actually two types of velocity, two components of velocity: a velocity horizontal and vertical velocity. So the mass flow rate, to remind you, is the density of the fluid multiplied by the velocity multiplied by the area perpendicular to the velocity. So the area and the velocity are perpendicular. So I can get the mass flow rate between, so let's say I have two streamlines. That's a good example, and the velocity is purely in the horizontal in the x direction. So I can get the velocity between those 2 points, and the distance between them is let's say y, and the width into the page is b. Then I can compute the mass flow rate. The mass flow rate is just the density. The mass flow rate going through this height y is just the velocity u multiplied by y multiplied by b. So, and that's what we have. In fact, so if we had a uniform velocity, that's what we will do. But if we have a non-uniform velocity between along the y, then we have to integrate. So so what we do is we break this element into small dy's, and here I would have my y1 at the bottom, and at the top is my y2. So here's my y1, which is this point at the bottom. So the mass flow rate, and here the width into the page is L, so let's just use the notation L instead of B. So mass flow rate is rho VA, so divide by the density and divide by the width into the page L. So m dot over rho L is going to give, I'm going to get it through integration the u with d multiplied by dy, and then, so that's the elemental mass flow rate going through this dy here. So we're going to call it dm dot, and let's substitute for u with d psi dy, And so when you do d psi dy dy, the dy's go away, and you now integrate from y1 to y2 of d psi. So it'll be the value of the stream function at 1, which is psi 1, and the value of the stream function at psi 2, at y2, which is psi 2. So the mass flow rate per unit, so m dot has units of kilogram per meter, kilogram per second. Density is kilogram per meter cube. So that's the volumetric flow rate, m dot over rho. And so that's the volumetric flow rate per unit length. So if I have two stream lines in a stream function family, then if I know the value, and the stream functions have value, so this would be value 5, this would be value 4, then if I subtract the values of the stream functions, I'm going to get the volumetric flow rate per unit area. And that's something we covered in the previous lecture. And we said that the streamlines, so we covered it in a different way. We said if I have two streamlines, in one location our streamlines were separated by a distance L1, and another location by a distance L2, then our flow here is going to be faster than our flow at this location, primarily because the mass between two streamlines is conserved. And that's what this also comes to tell us. And then we can also get it, we can do the same with for a flow going purely vertically. So for this case, I have two streamlines, and I have x1 and x2, x1 and x2 here, and my velocity is purely vertical, v, and v varies along the x. And now I can relate the mass flow rate to the vertical velocity v, and you'll get the same story. It's the difference between the two values of the streamline, and because of the minus sign, it's here psi 1 minus psi 2 as opposed to the other case. So that's the stream function. It's a quantity. It's a function that will be showing up quite a bit when we talk about the potential flow theory. So another piece of information other than the stream function is the vorticity, and the vorticity comes with its circulation. So let's talk about vorticity at the time being. So what are we dealing with? We're dealing with an airfoil, right? And there's flow coming over this airfoil, and it negotiates its path around that airfoil. So that air coming around it has a velocity field. So we saw in this case two components of the velocity field, a vertical component in the y and a horizontal component in the x. So these are, and in three-dimensional case, my velocity at any point x, y, and z has three velocity components, Cartesian components in the x, y, and z. So the vorticity, which we want to define now, is related to the velocity field through the curl operator. So the curl operator, the del, is just d by dx I d by dy. So the curl is just the cross product of the del operator d by dx I, j, and k, and so that's the del operator, and my velocity is u, v, and w in the I, j, k direction. So the curl, the vorticity, is just the cross product of those two vectors. So if you try and cross product them, let's do this guy. Cross product of I time, so del cross v, the I with the I gives you a 0 in a cross product because they're not perpendicular. and the I with the J gives you a K, and the I with the K gives you a minus J. So you do this for all of them. So what you will get is this type of formula. So you have pairs of velocity gradients that are subtracted from each other after you rearrange everything. And now let's deal with the case where I have a two-dimensional flow, where I don't, my flow just varies. I only have two velocity components, so I don't have a W, and I don't have variation in the, so I don't have a W velocity. So when I don't have a W velocity, everything that multiplied with a K is just not going to exist. So that will go away, and that's going to go away. So in 2D, my vorticity vector is going to be out of the page, so that's why it's K. So you can use your right-hand rule. So that's sort of, if you use your right-hand rule, when you rotate counterclockwise, that tells you that the quantity you're looking at is out of the page towards you. So the circular arrow is in the plane of the page, while this arrow is coming towards you. So the rotational one is in the plane, and this one is coming towards you, coming out of the page. And that's why it's a K. So you start with the in-plane velocity components, U and V, and you end up with a third, you end up with the vorticity to be in the third Cartesian coordinate direction. And we can define something called the angular rotation of the fluid. In fact, the angular rotation of the fluid is easy to understand. It's just a fluid element that's rotating around its axis, and the angular rotation of the fluid is just half the vorticity vector. So the vorticity vector is related to twice the angular rotation of the fluid, and we can look at it in this slide. So here I have a fluid element. So this is my X, this is my Y, and this is a flow field. So there is this point A is moving at velocity U, and U horizontally and V in the vertical direction, so U and V. And because this velocity field is varying, so here if I want to show you this over here, this would be my fluid element, and there are different streamlines around it. So because the velocity field, I expect to have changes in the velocity. So so that's at location Y. At location Y plus dy, I can use the Taylor series expansion. So this is Y plus dy. My velocity will change by an amount of the velocity gradient multiplied by dy. And same thing with the vertical velocity, it will change with the x. So at this location, the velocity is v. At a location x plus dx, my velocity is v plus dv dx multiplied by dx. And let this move so that's at time t equals 0. And now at time t equal t plus delta t, my fluid element here at point A would move a distance u times delta t and v times delta t. However, at point B and point C, my point B is going to move not in tandem, but it's actually going to move slightly faster. So you're going to get this shape. So now my point A has moved to this new location. However, my point B has moved a further distance than what it was than point A in the horizontal direction. And point C also moved a further distance than point A in the Y direction. So you'll see the rectangle that we started with has now become a trapezoid. And we look at these so why did this happen? It's because there's a variation in velocity at the three or four corners of the three corners of my imaginary rectangle. So at point A was my reference, so it moved, but point C moved at a different rate and point in the vertical direction, and point B moved at a different rate in the horizontal direction. So my rectangle became a trapezoid. And the different rate is this guy, du dy delta y and dv dx delta x. So this dv dx delta x, you multiply it by the delta t, you get this distance of deviation from or deformation, distance of deformation of the cube. So that makes an angle delta theta 1 and delta theta 2 that are over here. And so the difference between those delta thetas gives me the deformation in the object. And if I do the delta theta over delta t, I get the angular rotation. So now you see how this is how the angular rotation of the fluid element is related to the dv dx and du dy. So here's your dv dx and here's your du dy. So you might want to spend a little bit more time on than we have just spent on it to fully absorb that concept. But at least I hope I showed you, at least in a hurry, that the angular rotation of a fluid element, so now you see it's being deformed, and that deformation is related to the gradients in the velocity that came from the curl of the velocity vector, which is the vorticity. So now we want to define a flow field. So when the curl is 0, then my flow is considered irrotational, and because which means that my fluid elements have 0 angular rotation. They don't rotate around their fluid axis. So let's look at this picture. So here is a case where my fluid element, this rectangle, it keeps its orientation undeformed. So you see, even though it turns left, it doesn't rotate around its axis. It maintains the same orientation. So as opposed to a case where so now we'll show a different case. So this fluid element does not rotate around its axis, so it doesn't have any angular rotation, which means that this flow signifies an irrotational flow. Now, and where would we find this flow? That will be the first slide in our next lecture, which is when we're talking about the potential flow theory. And I think we mentioned this in the past, where we're going to break our flow into the boundary layer, where we have a lot of rotation, a lot of effect of viscosity, and where we have sorry about that. So I touched the wrong button. So we have a boundary layer and a flow outside the boundary layer. So this irrotational flow exists outside the boundary layer, so far away from the wall of the airfoil or whatever aerodynamic object we are dealing with. And then the counter or the other part of this argument is that inside the boundary layer, our flow is going to be rotational because there's a lot of velocity gradient associated with the variation of velocity from the no-slip condition to the free stream velocity that we have seen before. So inside the boundary layer, you look at a fluid element as it moves along a streamline, it actually varies its angular orientation. So this fluid element is actually rotating around its axis as it's translating, while here it's purely translating without any type of rotation. So you want to make this differentiation between a rotational flow and irrotational flow. The rotational flow exists inside the boundary layer, while an irrotational flow would exist in the free stream outside the boundary layer. And here's your vorticity in 2D, so it's just a cleaner form than a previous slide. And if you have an irrotational flow, then dv dx minus du dy is equal to 0. Then the other quantity we want, so now we can, once we have found what the vorticity is, and imagine this is a snapshot in a region of the flow, and these are our streamlines, then I can pick any region inside my flow. So it could be inside the boundary layer or outside the boundary layer. And I want to see how much rotation there exists inside this large region. So in that region, I can just take all the fluid elements. So I break it into an infinite large of fluid elements, and each fluid element might have a vorticity or an angular rotation around its axis. This guy might be rotating counterclockwise. This guy might be rotating about its axis in a clockwise fashion. But if I want on average to see what's happening inside this dashed contour, I can just integrate the vorticity. So this is my vorticity, del cross V, over the area. And what that gives me is the circulation. That circulation tells me how rotational my flow is. So if my circulation was 0, I'd expect that there is no circulation in there. Now you can go, so this was an area integral of the vorticity, it's a surface integral, surface area integral. And we can use Stokes' theorem to go from, you can actually go from 3D to 2D to a line integral. So you go from an area integral into a contour integral over a line. So you just, over that contour, which I'm going to signify by the distance s. So s is along the contour, this ds is along this contour. So when you integrate the velocity v dot ds, so the velocity in the direction of the contour over a closed contour from point A, you go all the way down to point A, you're going to get the velocity vector. So here is a simple example. Let's say my contour is this rectangle. So this is distance capital Y, so that's still capital Y, and this is distance capital X, and this is distance capital X, and my velocity here is u1, and my velocity here is v1, for instance, and here it will be u2, and here it is v2. So I'm just going to follow the arrows that I have drawn, the direction that I have drawn. So I can compute the vorticity, the circulation. In fact, we can compute the vorticity. Just give me a sec here. We can compute the circulation around this contour, the rectangular contour, to be the integral v dot ds. We start from one point, continue over through the whole contour, go back to that same point. So I'm going to get u1 times x. So it's the integral, so it's the dot product. So because those two are in the same direction, so the dot product gives me a cosine 0, so that's 1. The vertical velocity here, v1, is perpendicular to x, so it doesn't contribute any circulation. So I get u1x plus v1y. So I'm following the arrows. So I'm believing this plot to be the velocities to be positive in the arrow direction, the u2, the v1, and the v2. So v1 times y plus, so you get the point, plus u2 times x, because it's positive because we're going along the contour, because it's a dot product between the u and the x, u2 times the distance x. plus v2 times y. v2 times y, capital Y. Okay. So that would be your vorticity, your circulation around this contour. And now you can actually use this in a smart way to get the vorticity. So if the circulation is the integration of vorticity, then you have already computed the circulation. Then you can say, well, my vorticity zeta is just the circulation over the area enclosed within this contour. So it's this surface area. So that's another way of doing it. And the units for circulation is meters squared per second. What are the units of vorticity? So the del has units of 1 over meter. This has meter per second. So this is 1 over second. And this is meter squared. So that's why you get meter squared per second. And then, so we talked about the family of stream lines to be a stream function. And then we talked about vorticity and circulation. And now we want to talk about another family of lines, which we are going to call the velocity potential. And the velocity potential is only defined for irrotational flow. So that's why it comes after the circulation, because for me to have, so I'll have zero circulation in an irrotational flow. That's the prerequisite to define a velocity potential. So the velocity potential is defined for an irrotational flow, and the irrotational flow exists outside the boundary layer in any aerodynamic problem. So that's what an irrotational flow means. Then I can write my velocity, if my flow is rotational, I can write my velocity vector as the gradient of the velocity potential, which is this. And because we've defined it only for irrotational flow, then I can rearrange and write that my I can write my velocity to be I can write my velocity to be the gradient of the velocity potential only for irrotational flows. So that's my V is del phi. So the three components of this is the U, V, and W. So that's Vz or W, if you will. The U is d phi dx, d phi dy, and d phi dz. So, and then in polar coordinates, cylindrical polar coordinates, you have the radial velocity component, the tangential, as well as the axial or the z velocity component. So that is our velocity potential. And if you need to go spherical, I don't think we are going to use it we're not going to need it in this course, but there it is. So the velocity potential only exists. We define it only for irrotational. We define it only for irrotational flows. So that is, the vorticity is 0, or the angular rotation of a fluid element about itself is 0. So irrotational flow is a potential flow. So you want to keep that in mind. So that's where the potential flow theory that we're going to deal with in aerodynamics comes from. So the first theory that we are going to consult is this potential flow theory. So we're sort of ignoring the boundary layer. We're saying it doesn't exist, and it does exist, but we're going to solve for our flow field and for our pressures and velocities in the absence of a boundary layer. So if I have my my velocity potential function, then I can derive my three velocity components, u, v, and w. So which comes to be as a very nice tool. So look at the example on page 182, 2.9. It's Please do look at that. And there are similarities between the stream function and the velocity potential. In fact, they're very related. So when you have an irrotational flow, a potential flow, then you can define a velocity potential, and the velocity potential lines would actually be perpendicular to the stream function. So it's easy for us to visualize the stream function. So imagine this is my airfoil here. This is my stream line. So the family of a stream lines is stream functions. So what is a line that's perpendicular to this? That's a line perpendicular. So that's 90 degree. So that's I've drawn here the stream functions, and this perpendicular line is the velocity potential. So I'm drawing the velocity potential in blue. So here it's like so something like this, and here it goes like so. So you get the idea of the stream functions and the velocity potential lines are perpendicular to each other. So this actually brings us to the conclusion of our revision of fluid mechanics, and we've introduced a couple of concepts that we haven't covered in fluid mechanics, which are the circulation and velocity potential. We've looked at the stream line before. We're familiar with it. So now this will allow us to now delve into the potential flow theory. So let's dive right through into it. And that is, you'll find it on as chapter 3 in your book. So it's in a new part 2. Okay, so here's a slide we have looked at before, but let's revise it one more time. So you have your airfoil. On that airfoil, you have a boundary layer that is so you have a boundary layer that grows over the airfoil. It's a thin region, and what we are going to do in the aerodynamic theory that we're studying in this course is, why are we doing all this in the first place? Well, because it all goes back to the aerodynamic theory predicts the aerodynamic forces on an object. So if we want to predict the aerodynamic forces on an object, so we want to know how our boomerang is going to travel through the air, or how a spin ball is going to spin and get into the goal, or whatever the object of study, or it could be an airplane wing, whatever it is. What generates these forces that create those effects that we are interested in, like a swivel ball or anything, are basically the pressure field acting on my object and the shear stress field acting on my object. So that's the basic fundamental idea that we want to cover. So now we want to predict what the pressure field, so that's the whole point. We want to predict what the pressure field is and what the shear stress field is around this airfoil. So this is my airfoil, and I need you to tell me what the pressure distribution around the airfoil is going to be. So that's the pressure distribution. So that's the whole story behind this course, or behind what we're doing. So I need to predict what the pressure distribution is for me to be able to get, and again, remember we said that the pressure contributes to both lift and drag. So that's the pressure field as a function of x and y all around the airfoil. And that's pressure. And I also want to predict around that airfoil what the shear stress distribution is going to be. The shear stress acts parallel to the airfoil, or to the surface, I'm sorry, to the surface area. Pressure is perpendicular and compressive, shear stress is parallel. So we have come up with a simplified theory. So here's your shear stress, which we have come up with a simplified theory, which is the boundary layer theory, which we have covered in a previous lecture. And the boundary layer theory applies in the region very close to the surface of the airfoil, which is affected by the no-slip condition. So there is a region of influence of the no-slip condition due to viscosity of a couple of millimeters from the solid object of the airfoil into the airstream. So those 2 millimeters or 2 centimeters or 20 centimeters depending on the size of your object is what we call the boundary layer. And we've seen that the boundary layer theory, there are 3 topics of investigation: zero pressure gradient boundary layers, adverse pressure gradient, and favorable pressure gradient. And we have only introduced the theory for a zero pressure gradient boundary layer, so that's a flat plate. And we were able to propose, or actually to propose in that theory formulae for the shear stress distribution, which we refer to them as the CF, the friction factor, or the drag coefficient for the total. So that's the local friction factor, which was related to the wall shear stress. If you go to the previous lecture, you'll see this. Or the drag due to friction, the viscous drag. So that we have covered. So now we know how to get the wall shear stress. At least we get an estimate of the wall shear stress. It doesn't have to be. So what we're doing in this course, we're not going to get the answer. At least we're going. So we're not going to be able to compute the answer exactly for an object, but at least we can. In the worst case scenario, we can look at the trend. So we can make conclusions that, okay, if I do increase this dimension on my object, I'm going to get a higher shear stress or a lower shear stress. So we can look at trends, but also we can get orders of magnitude. So I'm not going to tell you that the shear stress is going to be 2 Pascal, but I'm going to tell you it's not going to be 10 Pascal or 0.1 Pascal. So it's an order of magnitude. How many zeros are? I'm not going to tell you that it's going to be 2 or 3 Pascals. I'm not going to be able to differentiate that. The level of uncertainty is quite big, but at least in certain cases we might be able to get to an uncertainty of 10-20%. That's the best uncertainty we can get to. But in most cases, it's going to be more like an order of magnitude estimation, because this is a theory. We're simplifying the real thing. We're trying to get an understanding of what's going on. We are trying to get an understanding of what the trends of the aerodynamic force are going to be, and we're going to get an understanding of how to compute that trend, as well as in simplified cases we might get close to the right answer. Within maybe close, I mean 30-40%. That's very good, but not 10%. So that's the boundary layer theory, which we have covered before. It tells us we can now get a good estimate, well, a sort of an okay estimate of the shear stress over the object, and we did that for the fuselage of an airplane. So now the next bit for us to get the aerodynamic force is to get the pressure distribution. So how are we going to get the pressure distribution? That is what the potential flow theory is going to do for us. And that's why we needed to define the irrotational flow. So the irrotational flow takes us outside the boundary layer. So we're now in the potential flow. So then we defined, from the irrotational flow, we defined potential, the velocity potential function, which is only defined for irrotational flow. And then once we have defined those, from the velocity potential, we can get the velocity distributions. And once I get the velocity distributions, I'm going to use Bernoulli to get back to the pressure. So that's our game plan for this new chapter, which discusses the potential flow theory. I hope this picture is clear enough for you, so that we can proceed with the potential flow theory and how we are going to get the pressure field from the velocity potential and so on. So we will come to the details in the coming slides. So we will stop here and we will take it from this point at the coming lecture. Thank you for your attention.